Thank you. As you can see, this is joint work with Martin Kusera, Pedro Zankov, Marco Guarneri, and Martin Wedgev. So let's dive right in. The motivation for this work is this kind of a familiar situation where we have some input that is actually confidential. And then we have some query that we would like to run on the input to produce an output. And we are going to assume that the output will actually be public. So the issue here is that the public output will reveal information about the confidential input, and our goal is to somehow restrict the amount of revealed information, or the amount and also the kind of revealed information. So for one example, consider this genomic database. So we have 3 people inside this database, or the genomic data of 3 people: Alice, Bob, and Carol. For every person, we will have information about the single gene, and there are actually 2 alleles present for each gene, and each allele can be either red or green here. And there is this person that we'll call Dr. Eve that has some research question about this data. And never mind her name, we will assume that her intentions are actually good, but still Bob is a little bit concerned and doesn't want to make his data public. So one first naive approach to this problem is to just say, well, as Bob is concerned, we'll just censor his data. So the input is a database and the output is a database without Bob's data. The issue with this approach is that even though Bob's data isn't present in the database, because Eve is not a fool and she actually knows that Carol is the daughter of Alice and Bob. So Carol is in front and Alice and Bob are behind. And she also knows how these genes are genetically inherited. She can conclude that, well, that the red allele must have come from Bob. And so Bob's data is actually leaked, even though it's not present in the output. In general, Eve will be able to do some Bayesian inference. So on the left-hand side, you have, again, this situation where we start with the private data, we run the program, and it produces some output. And everything further to the right is what happens in Eve's mind. She has some prior distribution on how this data was generated, and we're going to assume that this is public information. And of course, she also knows the semantics of her program because she's written those. And using the prior and the program semantics, she can compute the joint prior on inputs and outputs. And given the outputs that we will tell her, she can then update her prior to get the posterior distribution over possible inputs. And this is the way Eve will reason. Now, we are going to restrict how much information Eve can obtain. There's this kind of privacy policy that we will be given an attacker belief delta program pi and this privacy policy phi. And this is just a statement that says, well, for any possible output that the program could produce, we're going to want to restrict the posterior probability of a certain secret. And the secret is just some event. And in general, there will be multiple policies like that. This kind of privacy policy was actually introduced in 2013 by a paper by today's session chair, Michael Hicks. So here is a more realistic example. Now Eve just wants to know how many red alleles are in the database. And the policy is also a little bit more realistic. Now not only Bob is concerned, but actually everybody in the database wants their data to be protected. In particular, we don't want to have a posterior of larger than 75% on the event that some of the persons has 2 red alleles. Now the question is, may Eve run this program? And the answer is, of course, no, because if the output would be 6, then this would actually reveal all alleles deterministically. So we would know that with probability 1, all the alleles in the database are red, because that's just the number of alleles that are there in total. So the question now is, how can Eve actually adapt her program? And this is not that obvious, because she will need to do some probabilistic reasoning in order to figure out how to change the program that it gets accepted, and for her to still be able to get some information. Also note that our privacy policy does not itself depend on the secret. So even though in the actual confidential input you only have 3 alleles, this possibility that it could return 6 needs to be taken into account, and therefore we cannot run the program. Good. So this is the original program, and as we said, this is rejected because it reveals too much information about basically any person in the database. So now what we could do is, well, we shouldn't know whether the output is 6, so let's just join it with 5. So this program will, if the output is 5 or 6, we just randomly output either 5 or 6, and therefore we won't be able to learn if we see an output 5 or 6 whether it was 5 or 6. So the two outputs are somehow conflated. And now the issue is that this is still not enough because Carol, which is the daughter of Alice and Bob, will need to have 2 red alleles if there are 5 alleles in the database in total, and so this is not enough. But we can continue like that and also add 4 to this equivalence class of outputs. And now it will actually be enough. So under the assumption that what is written there is our prior on any given allele having one of the 2 colors. Now this was a little bit tedious, and the goal of the current work is to just take some program that is being rejected using this definition of privacy policy and to just turn it into a new program that has some additional statements and this new program should be accepted. And at the same time, it should still allow us to get some information. The contributions of this paper are that we formulate some probabilistic inference queries that are sufficient for our purposes. And we formulate the automated privacy enforcement problem, which is what you've seen here, right? Then we have some computational complexity results on this privacy enforcement problem. We show optimal synthesis algorithms and the heuristic synthesis algorithm. We implement everything and evaluate it on representative programs. So first, let me show how we represent the input information. So this is the prior distribution, which is represented as a probabilistic program. So first, this function here shows our prior belief over some patients about whom we don't know anything more than it's just some patient. And so we just draw his 2 alleles from and there are 2 alleles for the probability distribution from the general population. Then here we have a function child. So this encodes what we know about somebody of whom we actually know the parents. So A and B are the parents of the child. And how we are going to produce the alleles of this child is we flip a coin for each of them to select the allele that is inherited. And then we'll shuffle them in order to forget which parent gave which allele to the child. And our entire prior for Alice, Bob, and Carol is just Alice and Bob are patients from the general population, and Carol is a child of Alice and Bob. Then we return the database, which is just an array of the 3 patients. And this is the program. This you have already seen. So this loops over all the patients and all the alleles and just sums up the number of red alleles in this helper variable, which is returned in the end. And finally, we can also express the secret. And this is just a Boolean function that for each patient tells us whether this patient has 2 red alleles. And we would want to bound the posterior probability of this function returning true in the interval 0 to 0.075. Okay. So now finally, using these ingredients, we can formulate these inference queries. So the first inference query just computes the prior probabilities of the different outputs. And the second query gives us the posterior probabilities of the secrets given that we observed a certain output. And our notion of enforcement, which is quite a common way of defining this thing, is that it's an equivalence relation over the possible outputs, such that in the end, we will only learn which equivalence class the output of the program lies in. So we could just pick one equivalence class per output, and then the enforcement would just be the unaltered program. Another thing we could do is put everything in the same equivalence class, and then we won't learn any information. And of course, there's a lot of things in between. And what we want to do is we want to satisfy the privacy policy, while at the same time extracting as much information from the database as possible. And the notions of optimality we have considered are permissiveness and precision. The permissiveness of an enforcement is just the number of different equivalence classes. So this is the number of different distinguishable outputs. And precision is the number of equivalence classes of size 1. So we only count those outputs that are not conflated with anything else. Because in some applications, maybe you don't think an output that conflates multiple possibilities is actually useful. Then we have the following complexity results. So this is assuming we already have the results of the inference queries. So for permissiveness, we have a theorem that says that the synthesis of an optimally permissive enforcement is an NP equivalent problem. So it's both NP hard and NP easy. And for an optimally precise enforcement for a single policy only, mind you, is possible actually in n log n time, where n is the size of the output. So here is an example of how optimally permissive enforcement could be encoded in an SMT solver. And because it's an NP equivalent problem, it's somehow natural to use an NP oracle to solve it. You don't need to understand everything that's on this slide. It's just for illustration. So given the program, the belief, and the privacy policy, we can compute the probabilities that we've mentioned before. Then using those probabilities, we can create this kind of constraint system. And over those constraints, we will maximize just the number of different equivalence classes. Then the SMT solver gives us some model, which we turn into, well, the result here, which is 0, 2, 1, 3. Okay. Then because SMT is sometimes slow, we also consider discrete heuristic for permissive enforcement. So in this graph, you can see the posterior probabilities for 2 different secrets, because in general, there can be multiple secrets, right? This gray box is the privacy policy. And what we want to achieve is that the posterior probabilities of both secrets for all the equivalence classes that we have will lie in this gray box. So at the beginning, we start with every output in its own equivalence class. So this is 0, 1, 2, 3. And as you can see, outputting 1 is already fine. So Eve doesn't learn a lot of information if what the output is 1. But for the other outputs, it's actually not good enough. So we will need to do something. And how we do that for the grid heuristic is just we pick the most violating class, which is this one here. And then we merge it with some other candidates that brings it close to being non-violating. Violating just means it's outside the gray box. And we merge those 2 classes into one, and then we repeat until we get something that enforces the policy correctly. Then I'm also presenting the optimal algorithm for precise enforcement, but this is quite, well, I mean, I don't think I have enough time to really explain everything in detail, but we'll go quickly through it. So one thing you can notice is that there is always an optimal output where only one of the classes is not a singleton. So only one of the classes has multiple outputs in it. So how we're going to start is by just picking all the violating classes, so everything that is red in the diagram, and merging them into one equivalence class. Now, if this equivalence class is non-violating, then we are done, and this is an optimal solution. And otherwise, we're going to assume without loss of generality that the class is actually violating by going above B. Otherwise, we could just flip everything around and proceed in the same way. Now, what we want to do is we need to merge some more outputs into this class C that contains multiple outputs, such that this condition is satisfied. And this is just saying the probability of the secrets, given that the output is in this class, needs to be at most B. And this is, if you expand it, equivalent to this. We can write this in this different way. And now you can see that we have this sum on the left-hand side where each term only depends on one of the outputs. And we want that this sum is below 0, so we're just going to pick the smallest outputs first. So the outputs that minimize this expression first. Of course, we still need to keep the outputs in this set that were merged in here. So that's why it's possible that by picking some more outputs, we will go below 0. Okay, so then our system is called the Spire. We have a full implementation under this URL. As the approach requires exact probabilistic inference, we've used the Psi solver for exact probabilistic inference. And we've used C3 from Microsoft Research as the MP oracle for the SMT constraint solving. And we have evaluated our approach on benchmarks from 3 scenarios. One is the genomic data that you're familiar with. The other one is political affiliations in a social network. And the first example is protecting location data. This slide shows the inference times using Psi just to get the outputs, the probability of the outputs and the conditional probabilities of the secrets. The x-axis is the first thing is the size of the input. The second thing is the number of different policies. The trend lines don't necessarily make that much sense, but you can see that it scales roughly exponentially. Then there's the SMT times for optimal synthesis, both for permissiveness and precision, again with the same interpretation of the axis. And because, well, this is quite slow, we also have we also investigate the scalability of the heuristic, and because it's just a quadratic algorithm, it scales to quite some number of possible different outputs. Okay, then we have also compared SMT solver solution, which we know to be optimal against the heuristic, and it did quite well. So actually, it just optimally solved many of the instances. For example, for medical or social location, we leave out here because SMT timed out all the time, so we don't really know which percentage of instances we solved optimally. And here is some other kind of number that you could be interested in. It's just the percentage of so it's the average percentage of the optimal number of classes that we find with the heuristic. And it's also quite high, so always over 90%. And for precision, actually, we didn't have any examples where the agreed heuristic produced something suboptimal. But in summary, so we are given the prior distribution over the input data. We are given a program pi, and we are given a few privacy policies. And the goal is now to synthesize an enforcement, which is just an equivalence class, such that the posterior outputs, given that you observe that some output was in the equivalence class, is within given bounds. Thanks for listening. So we have perfect.
So I have a question that for the policy using here, is there any composition property here? For example, I have one program, I synthesize it, satisfy this policy, and publish the result. I have another program, I synthesize it, also satisfy the policy. But when people looking at the outcome from these two programs, can you say anything about whether these two outputs will preserve the original policy, or is there any bound that how much more user can learn from these two outputs?
Yeah, I think there is no such composition property because you could have some correlation between the two outputs.
Right. And so in this case, does it mean that when I have a new program, I want to run over this data, I need to remember what are the previous programs I've run before, so that somehow can know that people cannot combine all the previous results, outputs to do some inferences.
So we have this Bayesian inference approach, right, which was about at the beginning of the talk here. Mm-hmm. So you can just use the posterior distribution here as a new prior after each query, and we have experiments on this in the paper. And then you can still enforce the bounds, but I don't think there's a very good way to express what you're doing compositionally.
Okay, thank you.
I have a question. I'm curious. So you used one kind of noise, if I understand it right, which is that you sample from this equivalence class, and that way you add uncertainty about which is the actual correct output. That's easy for specifying an algorithm. I wonder, are there other, for example, if you had continuous data, or if you like, for example, you're doing location queries and you're worried about nearness or something like this, where you don't have a set of discrete outputs that you're going to merge together in a class. Does the same approach still work, or is there a way to adapt it?
Yeah, I think we can adapt to continuous outputs by taking a maximum over, or just quantifying over all sets of outputs, or all measurable sets of outputs instead of single outputs. And in this paper, we just considered discrete sets of outputs. But I think it does extend to this setting. It's just the enforcement itself. Maybe the equivalence classes won't be a good model anymore.
And a follow-up, depending on how, it seems like in the example that you showed, you always add to the equivalence class sort of at the very end of your query. So you just do the query, you're about to return the output, and then just before then you might return a different output. You'll sample from this equivalence class instead. Is there any disadvantage to doing it that way? For example, if you were to add noise in some fashion earlier in the program, might you end up getting an overall better output, or does it not make any difference?
So I think the only difference is that maybe you waste some time by computing precisely which output you want, and then you throw away that information. But otherwise, I think if you just do the noise earlier, you will still, in the end, just get some set of equivalence classes. But
Okay.
possibly probabilistic ones. But okay, it's a little bit more general, I think. But you could also do the noise in the end, and then I think it doesn't really matter where you add the noise.
Okay, thanks. Okay, let's thank the speaker.